Hello, my name is Samantha Scales, and this is my Lab 4 report on oscillations. In this lab, I studied a mass oscillating on a vertical spring while also swinging in an arc. I used Tracker to extract position data from the video, then built a computational model based on the momentum principle and Hooke's law to predict the same motion. My goal was to see whether the model matched the real data and whether total mechanical energy was conserved. The lab relies on three core physics ideas. First is the momentum principle, which is the net force on the ball, which would be gravity plus the spring force, and this determines how its velocity and position update each time step. Second is Hooke's law. The spring force is proportional to how far it's stretched from its natural length and always points back towards its natural length. And then the third is the energy principle. As the ball falls, it loses gravitational potential energy but gains kinetic energy. As the spring stretches, energy shifts into spring potential energy. If only gravity and the spring act on the system, the total, which is kinetic plus gravitational plus spring energy, should stay constant. Here are my results. The model in blue closely matches the horizontal x motion with an average error of only about a centimeter. The vertical y motion originally had a consistent offset, but after correcting that, the error dropped to about 2 centimeters. On the energy graph, you can see the gravitational and spring potential energy, which is the red and green, swinging back and forth in opposite directions as energy transfers between them, while the total energy in orange stays essentially flat near zero the whole time. This confirms that the model conserves energy as expected. For this experiment, I analyzed a video of the spring mass system oscillating vertically while swinging in an arc. I used Tracker to mark the ball's position frame by frame, calibrating using a 1 meter reference stick visible in the video. Then I exported the X and Y position columns to a CSV file and imported that into my GlowScript model so I could compare the computed motion directly against what actually happened. The system here is just the hanging mass, and for the surroundings, it's the spring, which exerts the spring force, and the earth, which exerts gravity. And then I treated air resistance as negligible in the model. The mass was set to 0.402 kilograms, and then the initial position and velocity came directly from the first two rows of my corrected tracker data, which was negative 0.138 in the x direction and negative 0.751 in the y direction. And then my velocity came out to be zero since it's resting at the beginning. For the spring constant, I used the measured oscillation period and solved for k using t equals 2 pi square root m over k, which gave about 6.83 newtons per meter. The relaxed length came from a static equilibrium force balance, where the spring force exactly balances gravity, giving about 0.123 meters. From there, the code computed the stretch vector L and used it to calculate kinetic, gravitational, and spring potential energy at every step. Each iteration of the loop calculated gravity and the spring force, added them for the net force, and then applied the momentum principle to update the ball's velocity and position. The spring is redrawn to match the new position, and the energy values are recalculated so I can track how kinetic, gravitational, and spring energy change at every time step and confirm whether their sum stays constant. Comparing the model to the real data, the exposition match is excellent, with the model and experiment tracing the same repeating pattern. The main difference shows up in amplitude over time. The real data's oscillation shrinks gradually, while the model stays constant since the model has no friction to drain energy out of the system. So the two main sources of error are first that the model has no air resistance or friction built in, so it can't reproduce the amplitude decay visible in the real footage. And then second is that the tracker's frame-by-frame tracking naturally introduces small amounts of position uncertainty. For the what does it mean questions, is the energy principle satisfied? Yes. The total energy curve stays essentially flat near zero, confirming the model conserves energy since only gravity and the spring act on the ball. I also compared two period estimates from the tracker data. From the vertical Y motion, the period was 1.524 seconds, averaged over 5 cycles, and then from the horizontal X motion, it was 1.667 seconds, averaged over 4 cycles. These differ because the motion is really two behaviors layered together, the vertical spring oscillation and the horizontal pendulum-like swinging. each with its own natural frequency. Thanks for watching!